Have this opportunity to talk about some of my work in progress on doing dimensionality reduction of spectra from the Sloan Digital Sky Survey using autoencoders. And this is stuff that I've been working on with Andy Connolly at UW. And we've definitely heard a lot about dimensionality reduction and autoencoders in this conference, but just to keep everyone on the same page, I thought it would be useful to motivate why you might want to think about autoencoders by starting with a more basic method of dimensionality reduction that might be more familiar, which is principal component analysis. So here's kind of a classic example where, let's say you have a two-dimensional parameter set, you make a scatter plot, and it turns out your two parameters are correlated. If you do a principal component analysis on this two-parameter space, you get a orthogonal basis that lives in this space and tells you kind of a rank order of directions that explain the most variance that you see in this data set. And this can be useful as a dimensionality reduction technique because then you can choose to ignore everything except, let's say, the first PCA component and project your data down into this space. And now you've reduced kind of the inherent dimensionality of your data. And this projection is the linear projection that preserves as much of the variance that you see in the data as possible, and also allows you to do kind of the best reconstruction in a least squared sense that you can with a linear transformation. Now, of course, I can only plot 2 dimensions on a scatter plot like this, and PCA is not the most useful in going from 2 to 1 dimensions. But if you instead think about spectra, which can have thousands of resolution elements, you can do a similar procedure with PCA, which has been done before. And you, first of all, you get the mean spectrum that's seen in your data set. So maybe that looks like the typical galaxy that you see. And these basis vectors in spectrum space, you can plot them out and interpret them as eigenspectra. And maybe you want to try to interpret this first component as telling you about a lack of star formation because it's negative in the blue continuum and it's trying to suppress these nebular lines associated with star formation. And you can, this has the advantage that you know exactly what PCA is doing. If this component is increasing, you're just adding this eigenspectrum in with some linear coefficient. But it might get more difficult to interpret exactly what each of these components are doing as you get to higher orders. Still, it turns out that this dimensionality reduction can be very effective on spectra. Even just using the first 3 components in the PCA basis, you can make this projection that allows you to very easily separate early from late type galaxies and even extreme emitters. And so you've taken this spectrum that's thousands of resolution elements and found a summary of it with only 3 parameters that allows you to make this classification. PCA projection can also act as a denoising technique by keeping, if you have a large enough data set, the noise will probably tend to be in the later PCA components. They're not explaining most of the variance that's in the data. And so if you take your noisy spectra and project them to the first 10 components, you get a version of the spectrum that looks a lot like a denoised version of it. And that's because the vectors of this PCA basis are being determined using all of your spectra at the same time. One big disadvantage of PCA is that it's a strictly linear procedure. And so if you have features that are hard to capture with a linear combination of templates, like broad spectral lines, where it can be hard to describe the broadening of a spectral line with just adding together different templates, PCA can take a lot more components to give you an adequate reconstruction. As an example, here's the original spectrum in gray with a PCA reconstruction using 10 components in black. And you can see that even by eyes, it's not really matching the shape adequately. And you have to go to 20 components to get a better reconstruction. And so PCA has a lot of desirable characteristics, and I'd like to argue that autoencoders are kind of a nice way to generalize PCA in a nonlinear fashion. And this sort of diagram has popped up over and over, but I think it would be useful just to step through it a little bit. So an autoencoder is a neural network where you're training the network to reproduce the input that you give it. And in order to stop the network from just learning the identity function, you have this bottleneck in the middle. And so you train the network to minimize some sort of reconstruction loss. And because of this bottleneck, the network ends up learning some sort of compression of the data with fewer parameters, because it has to figure out how to reflect the information that's in your large feature space in some sort of smaller parameter space so that it can reconstruct it at the end. And this really is a nonlinear generalization of PCA, because if you imagined putting in neurons with purely linear activation functions, that actually has the same solution as PCA does. And so now we're just adding in neurons with nonlinear activation functions. One flavor of autoencoder is the variational autoencoder. And it has a nice Bayesian interpretation that I like, where you can think of the decoder part of the network as a generative model whose latent parameters are the neurons that are in this bottleneck that I'll call Z. And so this is a generative model. You feed in parameter Z, and it spits out some spectrum X prime. And if you think of your reconstruction loss as actually a log likelihood, this reconstructed spectrum is a spectrum that you can compare to your input and take account of the noise levels and everything, and think of it as a log likelihood, then as a good Bayesian, all you need to do is put some sort of prior on this latent parameter space Z, and you then get some sort of posterior out. Of course, especially with the decoder being some nonlinear neural network, it's not trivial to find what this posterior is. But you can change the encoder a little bit. Instead of having it output a single point in the latent space, you have it return a mean and a variance. You have it return a Gaussian to try to approximate this posterior that your decoder is implying. And it turns out if you can think of the encoder as doing variational inference. And if you do this, then you get kind of the classic variational autoencoder, which has a nice interpretation. And one property that variational autoencoders give you is that they tend to make the latent space, they tend to reduce the number of gaps that you see in the latent space and make behavior across the latent space more continuous. And what I mean by that is, here's a scatter plot of autoencoding the MNIST handwritten digits into a autoencoder with 2 parameters. And different digits are color-coded to be different colors in this space. And you can imagine taking one of your example 1s, finding where it lives in the autoencoder space, finding one of your example 2s and finding where it lives, and drawing a line in the latent space and ask the autoencoder to give you the reconstruction that corresponds to different points in this line. And then it'll give you kind of its best guess of what a hybrid between a 1 and a 2 is in this space. And it's doing so in a way that's informed by the whole distribution of data that you've given it. So I've started applying autoencoders to SDSS spectra. To simplify things, I've de-redshifted all of the spectra to their rest frames and rebinned them to a common wavelength coverage with 1,000 pixels. I'm using encoders and decoders with 2 layers each, and I'm encoding down to a latent space that has 10 parameters. And one result that shouldn't be too surprising is that if you compare an autoencoder with a latent space of 10 parameters to doing PCA with 10 parameters, you can get better reconstructions with the autoencoder than with PCA. And this makes sense because the autoencoder is nonlinear. It has more flexibility in its reconstruction. One cool thing to note is that for the most part, you get sort of moderate improvements in the least squared reconstruction loss that you incur. But you get the most gains for these broad-line quasars, which have these broad spectral lines that I talked about. And if we look at just one of these example spectra, at the top here, I've got a spectrum in the dotted black line and a autoencoder reconstruction that uses only 5 parameters for the entire spectrum in orange. And you can see that it's doing a lot better than a PCA reconstruction, which is in blue, with 5 parameters. Just like with PCA, if you look at the first 3 components in this autoencoder space, you get a nice separation of different classes of galaxies. It seems that the first autoencoder component on the x-axis is giving us this nice transition from absorption line and quiescent galaxies on the left to emission line galaxies on the right. And then the third autoencoder component is putting narrow line quasars just above the emission line galaxies and the broader line quasars further up. And as I talked about before, this autoencoder, because of the decoder part of the autoencoder, you can explore reconstructions in different parts of this latent space. And one thing you can do is to ask, okay, what is happening in this line that connects quiescent galaxies to emission line galaxies? And you can plot a series of synthetic spectra along this connected line and see kind of the smooth transition between these 2 classes. And so, this is doing more than just a simple interpolation in the spectrum space, but it's trying to give you its best estimate for how to transition between these classes based on all of the examples that it's seen in between. And so you can see, for example, the blue continuum rising up as we head towards an emission line galaxy, as well as these emission lines strengthening. Similarly, you can see how the autoencoder smoothly gives you spectral lines that go from narrow to broad, and also the changes in the continuum that seem to accompany this change in the data set. Another path that I think is interesting to look at is the one connecting emission line galaxies to narrow line quasars. And one thing you can do with these synthetic spectra is you can run all of the diagnostics that you're used to doing on observed spectra, like taking the equivalent width of lines and calculating line ratios. And so here are these 2 line ratios that have been used to classify emission line galaxies versus quasars. And so not only can you plot the autoencoder's synthetic spectra, plot a series of them, you can also do these diagnostics on the synthetic spectra and see how the autoencoder gives you spectra that start out in the emission line galaxy part of this diagnostic space, cross the diagnostic line, and then give you a narrow line quasar at the end. So to wrap up, autoencoders are an unsupervised method to learn compressions or representations of data sets. And you can think of them as a nonlinear generalization of principal component analysis. Because of this nonlinearity, they're able to give you better reconstruction performance than PCA with the same number of parameters, and they're able to handle nonlinear features like broad spectral lines. And I think this representation that the autoencoder gives you is very exciting. It seems to naturally separate out different classes of galaxies, and you can also generate series of synthetic spectra by drawing lines in this latent space and asking for reconstructed spectra from the autoencoder. And I think one big open question is how to fully make use of this latent space that the autoencoder gives you, how to interpret it, and also how to, I've shown you things that, classes of galaxies that we already knew about, but it might be powerful to know how to use this latent space to find things that we weren't expecting. Thank you.